Welcome to I Forever, Establishing Smart Living, the podcast where we dive into the fascinating world of artificial intelligence and explore how it's transforming our lives, one innovation at a time. Today, we'll embark on a captivating journey into the realm of AI through the lens of a groundbreaking research paper titled, "Attention is All You Need." This landmark 2017 paper, authored by 8 visionary scientists at Google, introduced the world to the transformative transformer model. It's no exaggeration to say that this innovation has revolutionized language processing, enhancing both efficiency and accuracy like never before. The transformer model is built upon the attention mechanism, originally proposed in 2014 by Bardanow et al., offering a dramatic leap forward in the field of machine learning. While the initial focus of this research was on refining seq-to-seq techniques for machine translation, the authors foresaw the broader implications of their work. They envisioned its potential to tackle other complex tasks such as question answering and what we now know as multimodal generative AI. This research paper is not just a technical marvel, but also a cultural nod, with its title cleverly referencing the iconic Beatles song, "All You Need Is Love." The name, Transformer, was chosen because the author Uscorite found it to have a catchy ring to it, a fitting choice for a model that has become the cornerstone of modern artificial intelligence, setting the stage for large language models including those based on GPT. I'm EV, a passionate technophile with nearly 20 years of experience in the IT industry. I served at a global consulting technology firm, specializing in AI and machine learning applied research and software development. My journey is driven by a deep fascination with technology and its transformative potential for our world. I'm thrilled to take you on this enlightening journey. Our mission is clear: to empower you, our listeners, by providing insightful analysis and real-world examples of AI technology. We aim to show you just how AI can enhance productivity, improve well-being, and seamlessly integrate into your daily life. Each week, we'll explore AI through several key series, each designed to give you a comprehensive understanding and practical knowledge. Our series includes self-improvement, mechanism, applications, review, and trends. Let's delve into what each series has in store for you. If you enjoy I Forever, Establishing Smart Living, please subscribe, like, and share our podcast. Leave us a comment to share your thoughts. Follow us on X and LinkedIn for updates and join our community by becoming a Patreon member for exclusive content and perks. Have a question or topic suggestion? Leave us a message. We'd love to hear from you. Empower your life with AI, one episode at a time. In the fascinating universe of artificial intelligence, one of the most intriguing areas has been teaching computers to understand and process language as we do. For many years, a type of computer model called recurrent neural networks, RNNs, has been the backbone of this effort. RNNs are like really smart machines that read sentences or sequences of words one piece at a time, much like following a detailed set of instructions or reading a novel word by word. While they're pretty good at remembering what they've read earlier in the sequence, they have some limitations, especially when it comes to handling longer sentences. It's as if RNNs get a bit overwhelmed trying to remember the beginning of a story when they're deep into the middle of it. To help RNNs handle these longer sequences better, scientists developed more sophisticated versions called long short-term memory networks, or LSTMs, and gated recurrent units, or GRUs. Think of LSTMs as having a special memory system that decides what is important to remember and what can be forgotten as they go along. For example, if you're baking a complicated recipe, LSTMs instinctively know which key steps to remember at any given time, like kneading eggs in the beginning and knowing when to preheat the oven, even if it's written pages later. They smartly filter out what's not needed right away, helping them to focus on essential instructions needed later. Similarly, GRUs are like the simpler, more efficient cousin of LSTMs. They streamline this process by getting rid of extra steps in the memory system, making them faster and somewhat easier to train. Imagine a GRU as a savvy cook who's made this pie a dozen times before and efficiently recalls the major steps without getting bogged down by every minute detail. However, all these models share a common challenge. They process words one by one, in order, which means they can't really speed up this reading process or take in everything at once. Imagine if you could only read one word at a time before going on to the next, and couldn't skip back and forth easily in the text to gain context. This linear method can become a bottleneck, especially when you're dealing with long and complex texts. This is where the transformer model comes into play, a revolutionary shift introduced to overcome the limitations of these earlier methods. Instead of reading word by word, transformers use an attention mechanism that allows them to look at every word in a sentence at once, sort of like having a superpower that shows them the entire sentence at the same time. It's akin to reading the whole instruction manual in one glance, understanding the big and small picture concurrently without flipping page by page. The innovation with transformers is that they dispose of the need for sequence-based processing entirely. This allows computing processes to run much faster and more efficiently, reducing the time and resources needed to train these AI models. By using attention, transformers can connect the dots between words spread across the sentence more effectively, capturing the context and meaning more accurately. This breakthrough means that language translation, understanding and processing by AI can be done more quickly, effectively, and with less computing power. It's like turning a slow, methodical process into a rapid, intuitive understanding, akin to how an experienced chef instinctively knows the recipe without checking the cookbook every minute. The transformer model signifies a new era in the realm of AI, paving the way for further innovations and adaptations. In the groundbreaking paper, "Attention is All You Need," the authors introduced the transformer model, which revolutionizes the way machines process sequences of data, such as sentences in a language. Let's simplify and delve into the innovative aspects of this model. At its core, the transformer model relies entirely on the concept of attention, which allows it to process and understand language more effectively. To grasp this, imagine trying to understand a sentence by seeing all the words at once rather than reading word by word. What's more, you'd also be able to weigh the importance of each word depending on its context and meaning in the whole sentence. This is essentially what attention in the transformer model does. In typical models, like recurrent neural networks, RNNs, sentences are processed one word at a time. This is a bit like trying to solve a puzzle where you add one piece at a time. It works, but it can be slow and cumbersome. In contrast, attention allows you to see all the pieces at once and understand where each fits. The transformer does not use traditional methods, such as recurrence or convolution, which are akin to stitching together a knitted scarf, connecting one loop at a time, or rolling a paint roller over a wall, covering large continuous patches at once. Instead, it takes a more holistic approach. Here's an everyday example to illustrate how this attention mechanism works in the transformer. Imagine you're preparing a dessert, say, a fruit salad. Each piece of fruit represents a word in a sentence. Attention is the ability to simultaneously see all the fruits in your dish, understanding which pieces should be prominent, perhaps the juicy strawberries, and which ones add just a hint of flavor, like the dash of lemon. This allows for a balanced and tasty dessert with all pieces working together harmoniously. The innovation doesn't stop at just attention. The transformer introduces multi-head attention, which works like a team of chefs each looking at the recipe from a different angle. One chef might focus on how sweet the batch is, while another checks the acidity. By combining these insights, they create a perfect dish. Similarly, multi-head attention enables the transformer to capture various aspects of the sentence, making its understanding richer and more nuanced. Additionally, the transformer model uses something called positional encoding to keep track of the order of words. Imagine giving each piece of fruit a number to remember the order in which they were added to your fruit salad. This way, the transformer model retains the sequence information despite its nonlinear approach. Unlike RNNs, where the order dictates how quickly you can add each puzzle piece, or word, the transformer allows for parallel processing, significantly speeding up training time. Consider it like having an assembly line at a factory rather than a single worker building a product from start to finish. Efficiency is greatly boosted. By using such innovative features, the transformer model handles tasks like language translation with unprecedented quality and efficiency. It's as if it can simultaneously read and understand a complex book and then translate it into another language instantaneously, providing insights and context that previous methods might miss. In essence, the transformer model's reliance on attention and parallel processing not only makes it a faster and more effective approach for tasks involving sequential data, but also opens the door for broader applications, such as in image and audio processing, similar to how artificial intelligence can now help identify objects in photos or even understand voice commands on your mobile phone. We delve into the intricate workings of the transformer model, a groundbreaking approach to sequence transduction that eschews traditional methods in favor of attention mechanisms. Let's break down this section into bite-sized, everyday analogies to make it more digestible. At its heart, the transformer model consists of an encoder-decoder structure, a bit like having two teams working together to complete a task. The encoder team takes in all the information and processes it, while the decoder team takes that processed information to produce the final output. This process is akin to a game of telephone, where information is passed along and refined, but with the benefit that all parts of the message are easily accessible from start to finish. Think of the encoder as a team of 6 identical members, each with well-defined roles. Each member performs the same set of tasks, focusing on understanding different parts of the input. Each layer in the encoder has 2 main subtasks, much like a chef preparing ingredients before cooking. Multi-head self-attention. Imagine this as a chef tasting each ingredient, determining its flavor and deciding how much of it will contribute to the final dish. This mechanism allows the model to weigh different parts of the input sequence, understanding which words are more critical based on their context. Feed-forward network. This is equivalent to blending the ingredients to create a well-balanced dish. The layer takes the weighed inputs and adjusts them, ensuring all flavors are balanced, making sure the resulting output is cohesive and meaningful. Both these actions are equipped with residual connections, akin to a chef checking each step against the original recipe to ensure consistency, and layer normalization, which helps stabilize the process, similar to constantly tasting and adjusting spices in a pot of soup. The decoder is similar to another set of 6 layered chefs, but with an additional task, because they not only process the encoder's output but also generate the final translation. They have an extra sub-layer, masked multi-head self-attention. Consider this a secret taste test, where the chefs must decide the next ingredient, word in a sentence, without seeing the future items. This masking prevents any peeking ahead, ensuring that predictions are grounded only in what's being processed so far. Encoder-decoder attention. Imagine here, the chef consulting the initial checklist made by the encoder team to ensure every taste, context from the input, is considered in the final dish. This cross-attention means every part of the output is informed by the complete input, much like referring back to a complete list of ingredients while cooking. This dynamic allows them to generate the final output sequence, one element at a time, effectively converting the transformed input into something new and coherent. Attention in the transformer is like a superpower, allowing the system to consider every word in a sentence simultaneously and weigh their importance relative to one another. This global view is crucial for understanding context. For instance, in the sentence, "The cat sat on the mat," attention helps decide which words contribute most to the sentence's meaning based on their relational context. This method is much like using a set of binoculars, queries, keys, and values to adjust focus and bring different words into sharp relief. Each word is like an object in different layers of scenery, and the attention mechanism identifies which objects, words, to focus on for clarity based on their importance. Imagine multiple pairs of binoculars, each focusing on different parts of a scene. Together, they provide a comprehensive understanding of the landscape, sentence. Multi-head attention allows the model to assess various sub-aspects of the input data concurrently, enhancing its understanding of nuances and relationships across different parts of a sentence. Since transformer models ignore the sequence in processing words, they need to understand word order. Positional encoding is like adding little tags or GPS trackers to each word, indicating their place in the sequence. This ensures that "the cat sat on the mat" doesn't become "on the mat sat the cat," preserving the intended meaning. What makes the transformer innovative is its ability to process all parts of the input simultaneously, akin to having multiple people work on a jigsaw puzzle together, instead of one piece at a time. This allows for much faster processing, which is crucial when working with large datasets. By embracing a fully attention-based approach, the transformer model achieves a level of efficiency and accuracy that was previously difficult to attain. It represents a significant leap forward, not just for language processing tasks like translation, but potentially for any applications that require understanding complex sequences of data, ranging from video processing to even analyzing complex financial data. Authors discuss the impact and results of the transformer model, which has redefined how AI systems understand and process language. Here, we'll explore these impacts and results by using everyday examples to make them more relatable and understandable. Before the adoption of the transformer model, the world of machine translation and language processing was dominated by models like recurrent neural networks, RNNs, long short-term memory, LSTM, networks, and gated recurrent units, GRUs. These models work by processing words in a sequence, much like a person reading a book word by word. While effective to a degree, these methods had significant limitations, particularly in managing the complexities of longer texts. Imagine trying to recite a lengthy poem by memory, where each preceding line affects your recall of the next. Over time, the earlier parts can become fuzzy, impacting the overall comprehension. The transformer model, however, adopts a completely different approach that leverages attention mechanisms, allowing it to consider all words in a sentence at once. Think of it as opening a book page and looking at it entirely, rather than following each word with a finger. This innovation results in significant advantages in both speed and comprehension, enabling the model to understand context more effectively and translate languages more accurately. Parallelization leap. One of the most groundbreaking outcomes of the transformer model is its ability to operate in parallel rather than sequentially like its predecessors. To conceptualize this, consider a banquet preparation process. Traditional models would be like preparing each dish one after another, which could take an extensive amount of time. The transformer, in contrast, allows multiple chefs to prepare different dishes simultaneously. This approach drastically reduces the time required to complete a task, making the transformer much faster at training on large datasets. Improved contextual understanding. The use of attention mechanisms allows transformers to better grasp the context, akin to having a team of editors assessing an article, each with a deep focus on different sections but collaborating to enhance the overall narrative. This ability to attend to all parts of a sentence enables the transformer model to achieve more accurate translations as it captures subtle nuances and relationships between words that previous models might miss. Scalability and versatility. The transformer model is highly scalable, which means it can be trained with large datasets much more efficiently than older models. Imagine updating and training staff in a fast food chain with revised procedures. Having a system that allows everyone to learn simultaneously rather than individually saves time and ensures consistent quality. With this scalability, transformers are adaptable to a wide range of language processing tasks, extending their utility beyond simple translation to include tasks like summarization, sentiment analysis, and more. The results presented in the transformer paper validate these advantages dramatically. When applied to machine translation tasks, the models achieved state-of-the-art performance, beating previous benchmark scores by a significant margin. For instance, on the WMT 2014 English to German translation task, the transformer achieved a blue score of 28.4, outperforming all predecessor models, even those that combined multiple models together to enhance their performance. To put this into perspective, think of Blue as a school grading system for translations where a higher score reflects a better understanding and translation of the text. The transformer, in this instance, not only topped the class but did so using fewer resources and in less time. Similarly, in the WMT 2014 English to French task, the transformer achieved a Blue score of 41.0, establishing itself as a new standalone leader in translation quality. This is akin to setting a new record time in a marathon while running with less training and fewer support mechanisms compared to previous winners. These impressive gains are not only academic, they translate to economic and practical benefits, especially in commercial applications. Training times for the transformer are significantly reduced. It can achieve stunning results in as little as 12 hours with fewer computational resources than traditional methods. This efficiency is comparable to needing fewer cooks in the kitchen to deliver a full menu faster and with superior taste, thereby cutting costs and enhancing productivity. Moreover, given that transformers can be trained quickly, they hold the promise of being adaptable to real-world updates, such as new slang in languages or changing linguistic patterns, with minimal downtime or retraining efforts. This adaptability enhances the model's practicality in dynamic environments where language evolves rapidly, such as social media monitoring or real-time communication translation tools. Beyond just translating languages, the success of the transformer model has implications across various fields that require sequence modeling. This includes speech recognition, image processing, and even analysis of temporal data like financial trends or weather patterns. Think of it as introducing a versatile kitchen appliance that doesn't just chop vegetables but can also knead dough and juice fruits, revolutionizing culinary preparation entirely. The transformer has set a new standard for sequence transduction models, inspiring subsequent models that have built on its foundation to further enhance AI's capabilities. Models like BERT and GPT, which are based on transformer architectures, have furthered language understanding to new heights, proving that the adoption of attention mechanisms is indeed a transformative leap in AI research and application. In conclusion, the transformer model's impact is vast and multifaceted, advancing how machines understand and process human language in unprecedented ways. Its efficiency, accuracy, and scalability make it a compelling choice for any application requiring rapid and sophisticated sequence modeling, marking a significant milestone in the evolution of AI technologies. Attention is all you need highlights the significance of the transformer model as a pioneering approach in the realm of sequence transduction models. This model departs from traditional architectures by discarding recurrent layers, which have typically been integral to neural network models used for tasks like machine translation and language modeling. The transformer model introduces an architecture that relies entirely on self-attention mechanisms, eliminating the need for recurrence and convolution. This change in architecture brings about several advantages. Firstly, the elimination of sequential processing constraints allows for significant parallelization. This means that instead of processing sequence data one step at a time, like reading a book word by word, the transformer can consider the entire sentence simultaneously. Such parallelization is crucial as it dramatically reduces the time needed for training complex models on large datasets, thereby enhancing computational efficiency. By focusing solely on attention mechanisms, the transformer achieves improved translation quality. On tasks such as the WMT 2014 English to German and English to French translations, the transformer model has set new benchmarks, significantly surpassing the best results achieved by previous models, even those using ensemble techniques. This achievement underscores the model's capability to handle complex language tasks effectively. The implications of the transformer are broad and far-reaching. The model not only advances the field of natural language processing, NLP, by providing a more accessible and efficient method of training and deploying language models, but also encourages the re-evaluation of current approaches to sequence modeling. The success of the transformer paves the way for exploring attention-based models in a variety of contexts beyond language, such as video processing, speech recognition, and potentially any task that can benefit from understanding sequences of data. The authors are optimistic about the future of attention-based models and plan to extend this architecture to applications involving different input and output modalities, beyond just text. This flexibility could lead to innovative solutions across multiple domains where understanding patterns in sequences is vital. Moreover, they highlight the potential of local, restricted attention mechanisms to efficiently manage large input and output sequences, such as those found in image and audio processing. One of the envisioned research goals is to reduce the sequential nature of generation tasks further. The vision is to develop models that can generate outputs more fluidly and naturally, akin to how humans process and produce language. The transformer represents a significant leap forward, showcasing how eschewing traditional constraints can lead to innovative breakthroughs that redefine efficiency and performance standards. By relying on attention mechanisms, the transformer sets a new paradigm for sequence processing tasks, laying the groundwork for future research and applications that leverage its principles. In summary, the transformer model redefines how AI systems can efficiently and effectively model sequences, emphasizing parallelization and the potent capabilities of self-attention. Its achievements in translation tasks highlight its role as a transformative force in AI research, paving the way for new explorations and applications across diverse fields, and promising to elevate our understanding of complex data sequences. This brings us to the end of today's episode. We've delved into the transformative power of the transformer model in redefining language processing and sequence transduction, shedding light on the remarkable advancements in AI technology. To recap, we explored how the transformer model, relying entirely on attention mechanisms, surpasses traditional models by offering parallel processing capabilities, improved translation quality, and increased efficiency. This innovation paves the way for numerous applications beyond language translation, promising to reshape various industries with its versatility and speed. I encourage you to reflect on how these advancements in AI could impact the fields you're interested in or are working in. Whether it's in language, image processing, or even video analysis, the opportunities are boundless. If you're intrigued, dive deeper into the topic or explore the resources linked in the episode description. Remember, while AI is a powerful tool, it's important to continually consider its ethical implications and applications thoughtfully. Thank you for joining me on this inaugural episode of AI Forever, Establishing Smart Living. If you found value in today's discussion, please subscribe to the podcast, leave a review, and share it with your friends and family. Until next time, stay curious and keep innovating. I'm EV, and this is AI Forever, Establishing Smart Living.